So good morning, students. We'll be starting with a new chapter, spectroscopy, that too absorption spectroscopy. And this is the first of your spectroscopy chapters. So we will start with introduction to spectroscopy. I think you must be familiar with the word spectroscopy because you would have studied in your school days. But I'll just refresh your memory about spectroscopy, and then we go on to absorption spectroscopy, UV visible spectroscopy. So these are the topics that will be covered. Properties of light, which you may be familiar with, electromagnetic radiation and electromagnetic spectrum, what they are, then the absorption of light, because we are dealing with absorption spectroscopy, then Beer's law. This is a law that is extensively used in this method. Limitation of Beer's law. So how we can get over the limitations also we'll be seeing. Absorption of light by molecules. The instrumentation part, that is the various instruments used in absorption spectroscopy, particularly concerned with UV visible region. Applications of this, and finally one of the applications, that's spectrophotometric titration in detail. So these are the topics that will be covered in this chapter. This is a very vast chapter. So we'll be going first with the introduction to spectroscopy. So what is spectroscopy? It's a branch of science dealing with the study of interaction of electromagnetic radiation with matter. So in other words, when electromagnetic radiation falls on matter made up of molecules, okay, molecules, atoms, electrons, protons. So when electromagnetic radiation falls on molecules, then what happens to the electromagnetic radiation? What are the changes produced in the molecules or the matter? Studying these things is what is spectroscopy. So you could basically broadly classify spectroscopy as absorption spectroscopy and emission spectroscopy. So our chapter today deals with absorption spectroscopy. You will be studying about emission spectroscopy also in some other chapters like flame photometry, fluorimetry. So that time you'll be concentrating on emission. At present, we'll be dealing with absorption spectroscopy. So the most important term is absorption. So what is absorption in spectroscopic nomenclature we'll be seeing subsequently. So since we mentioned in spectroscopy definition a term electromagnetic radiation, interaction of electromagnetic radiation with matter. So what is electromagnetic radiation? It's a form of energy that is propagated at very high velocities. It's many times compared with sound waves because electromagnetic waves are also, or electromagnetic radiation is also many times called electromagnetic waves. So it's compared with sound waves, but the major difference between the two is electromagnetic radiation can pass through vacuum, but sound waves need a medium for propagation. So electromagnetic radiation is characterized by dual nature. There are two theories which basically describe electromagnetic radiation. That's the wave theory. This is the classical theory and the particle theory. So these two theories we will go in detail. So according to wave theory, what is electromagnetic radiation? It is comprised of an oscillating electric field and a magnetic field. You can see in this picture here, you see electric field wave. Okay, this is the electric field, the red one, and magnetic field, the blue one. So blue one is oscillating in the x-axis, red one in the y-axis, and you also see this black arrow. This is the direction of propagation of the wave. So it is comprised of an oscillating electric field and a magnetic field with their corresponding vectors at right angles to each other and to the direction of propagation. This is the vector of electric field, this is the vector of magnetic field, this is the direction of propagation. This is the how electromagnetic radiation is described by the wave theory. You also see the other picture here. So if this is a wave, then this height of this wave is will be called the amplitude of the wave. And you can see this is a crest, this is a crest, this is called the wavelength. These are called the troughs. So we'll come to wavelength a little later. Okay, we have the wavelength here. So the wave parameters. Now we are talking about wave theory. So there are a number of parameters which are called wave parameters, which describe the electromagnetic radiation. The first one, most commonly used, is the wavelength. It is denoted by the Greek letter lambda. So wavelength is denoted by lambda. Lambda stands for wavelength. What is wavelength? The best way to define wavelength would be the linear distance from one point of a wave to the corresponding point on the adjacent wave. So important things here is linear, then corresponding point, adjacent wave. Now generally you can see in this picture here, wavelength is given here, that is peak to peak. Okay, so the distance from one peak to the next peak, or from trough to trough. Which trough? From one trough to the next trough. Or it could be from any point on one wave to the corresponding point on the adjacent wave. Now here I would like to tell why this linear distance, linear word is important. Now say from this peak to this peak, you can also take the distance like from here, you go here, you take like this, a circuitous route. So if you take the distance like this, it will be more, and you may say the wavelength is more, but that's not the right way. You should take the shortest straight line portion. You should measure it in a straight line. That's why the linear term is here. From one point of a wave to the corresponding point on the adjacent wave. See, here, this is also a peak. This is a peak. This is a peak. So if you say from the distance between two peaks without using the word adjacent, then what it means, it could be from this peak to this peak also. That's why the word adjacent is important. It should be the next peak itself. Or trough to trough. It could be from this trough to this trough. You can take the meaning like that also, if you don't use the word adjacent. Now, one point of a wave to the corresponding point on the adjacent wave. So here it is a peak. So to the next peak. You don't go from this to here. It is not, this is not a corresponding point for this. Peak to peak, trough to trough. And anywhere you start here, it will be a straight line, and this is the corresponding point. Similarly, from here to here. So this corresponding point means same at the same amplitude. So here, if you have, this is your zero axis, this is the amplitude, same will be the amplitude here. So if you measure at this point, this is the amplitude, same is the amplitude here, same is the amplitude here. Then you are having a corresponding point. This is the descending part of the wave, this is the descending part of the wave. So from here to here, you cannot take from here to here because it's not the corresponding point. I hope this is clear. So it's always best to define wavelength like this. The linear distance from one point of a wave to the corresponding point on the adjacent wave. Okay, if you don't remember this, the best would be to write the distance, linear distance from one peak to the adjacent peak. At least that you should be able to write, but always the best definition is what I have given here. The dimensions are the length units, because we are talking about distance. So you can have units like meter, centimeter, millimeter, micrometer, nanometer, and angstrom. What's the relation between all these units? 10 angstrom. Angstrom is the smallest unit, meter being the largest unit. So 10 angstrom equals 1 nanometer. 1 nanometer is also called millimicrons. So some books you may see it as millimicrons, some books you may see it as nanometer. More commonly used is the nanometer, but this is also used and there's nothing wrong in using it. So the 1 nanometer or 1 millimicron. This 1 nanometer equals 10 raised to minus 3 micrometer. Because this is a bigger unit compared to nanometer, we are using 10 raised to minus 3. It should not be 10 raised to 3. Suppose you say 1 micrometer equals how many nanometers? It will be 1 micrometer equals 10 raised to 3 nanometer, because nanometer is the smaller unit. Okay, I hope it's clear. 1 nanometer equals 10 raised to minus 6 millimeters. So the difference between these two is again 1000. Okay, so 1 micrometer will be 10 raised to minus 3 millimeter, or 1 nanometer will be 10 raised to minus 6 millimeters. 1 millimeter is 10 raised to minus 1 centimeter. So you add one more. So 1 nanometer is 10 raised to minus 7 centimeter. And 1 centimeter is 10 raised to minus 2 meters, so you add another 2. So 1 nanometer is 10 raised to minus 9 meters. That's how you get this relationship. You should be very clear about this. If you are told to convert from one unit to another unit, you should be able to do that. Now, electromagnetic radiation could be of two different types. It could be monochromatic radiation, or it could be a polychromatic or heterogeneous radiation. What does that mean? Because we'll be frequently coming across this term in our instrumentation of spectroscopy, where generally monochromatic radiation is used. So what is monochromatic radiation? It's a radiation having one discrete wavelength. It's a radiation having one discrete wavelength. That is, all the rays are having the same wavelength. Polychromatic radiation means a number of wavelengths are present in a beam of radiation. So several wavelengths are present, then it's called polychromatic radiation. So when a lamp emits radiation, it is always polychromatic radiation. Absolutely monochromatic radiation can only be emitted by lasers, because lasers emit radiation having only one wavelength. So that's monochromatic radiation. The second wave parameter describing electromagnetic radiation is frequency, and it is denoted by nu. Okay, it is denoted by the Greek letter nu. What is frequency, or how is it defined? As the number of wave units passing a given point in unit time, or passing a given point per second. So in 1 second, how many wave units pass through a given point? I'll just show you what is a wave unit. One wave unit is, suppose you're starting from this point, this till here is one wave unit. One crest followed by one trough. This is one wave unit. So how many of those wave units pass a given point in 1 second? That gives the frequency. Units of frequency are cycles per second, or nowadays it's hertz. Hertz short form is Hz. So 1 hertz equals 10 raised to minus 3 kilohertz, or 10 raised to minus 6 megahertz. So any of these could be used depending upon the frequency. If the frequency of radiation is very high, we go to the higher units like kilohertz and megahertz instead of having very large values. The next parameter is wave number. So this is wave number of waves, it is nu bar. So it is denoted by the Greek letter nu, and on top you have a line, nu bar. Number of waves per centimeter in vacuum. This is called wave number. Its unit is centimeter inverse because it is per centimeter. Wave number is the reciprocal of wave length. That is, nu bar equals 1 by lambda. This wave number is more commonly encountered in IR spectroscopy. There we describe electromagnetic radiation in terms of wave number. In case of UV visible, we describe in terms of wavelength. In case of NMR, we describe in terms of frequency. So it is different for different types of spectroscopy. And lastly, we have the fourth wave parameter, that's velocity. So what is velocity? It's the product of wavelength and frequency. Unit is centimeter per second or meter per second. Velocity is given by small v, which equals lambda nu. So nu is the frequency, lambda is the wavelength. Frequency of radiation is determined by the source emitting the radiation. So wavelength of the radiation will change when velocity changes. So with different wavelengths, velocity will be different. So if you have a radiation with a different wavelength, then the velocity through the same matter would be different. So the velocity of electromagnetic radiation decreases when it passes through a medium. So whenever electromagnetic radiation passes through a medium, the velocity will decrease depending upon the density of the medium. The more denser, more the electrostatic interactions with the matter, and more would be the decrease in velocity. So the velocity would be maximum in vacuum, and in vacuum the velocity becomes independent of wavelength. Or in other words, all electromagnetic radiation, whatever the wavelength, whichever region they belong to, they have one maximum velocity in vacuum. So velocity through vacuum is denoted by c. Small v is used to denote velocity through a medium, and velocity through vacuum is denoted by c. So c is also equal to lambda nu. C has a value of 2.99792 into 10 raised to 8 meter per second, which you can approximately take it as 3 into 10 raised to 8 meter per second. Or if you take in centimeter per second, it is 2.99792 into 10 raised to 10 centimeter per second. This you must be knowing as velocity of light, but this is velocity of light in vacuum. So the second theory, that finishes the first wave theory, the classical theory. Now it is the second theory which we'll discuss, that's particle theory. Electromagnetic radiation is made up of a stream of discrete packets of energy called photons. This is what particle theory states. Electromagnetic radiation is made up of a stream of discrete packets of energy called photons. So what are photons? They are packets of energy having a definite amount of energy, and a stream of these photons makes up the electromagnetic radiation. Each photon has a definite energy which may be absorbed or emitted when electromagnetic radiation interacts with matter. So whenever there is an interaction, suppose absorption is taking place, then the entire photon energy has to be absorbed by the molecule or atoms or electrons. So it cannot be like part absorption. So a photon has a definite energy E, then the full energy has to be absorbed. Half the energy or 1/4 the energy, like this, fractions cannot be absorbed. Now we also, in particle theory, there is another term which is called intensity of radiation. Intensity of radiation indicates the number of photons that are propagated in the beam. Please understand this. This has got nothing to do with energy. Intensity of radiation indicates number of photons propagated in the beam. The photons could have different energies. So intensity is not dependent on wavelength, frequency, or energy. It only depends upon the number of photons. So now, one simple example is, you all are very familiar with UV radiations, and you are also familiar with X-ray radiation. You know X-ray radiations have got greater energy. So if you have two beams, one X-ray radiation, one UV radiation, the energies are different. X-ray having the higher energy than UV. But can the intensities be the same? Yes, the intensities can be the same. Or the intensity of X-ray can be greater than the UV, or intensity of X-ray beam could be less than that of UV also. All the possibilities are true. This is because intensity depends on the number of photons. If the number of photons in the X-ray beam equals the number of photons in the UV beam, then the intensities are same. But the photons in the X-ray beam will have greater energy. Though there are 10 photons in both of them and the intensity is same, each of the 10 photons in X-ray beam will have a higher energy than the photons in UV beam. I hope now intensity of radiation is clear with you. So now we see the relationship between particle and wave parameters, because both the theories have been found to describe certain features about electromagnetic radiation. Most of the phenomena associated with electromagnetic radiation and spectroscopy is explained by the wave theory, but particle theory is necessary to explain particularly the absorption and emission phenomena. And that's why we consider both the theories to be complementary to each other. And they are taken together. So what is the relation between these two parameters? Consider a given frequency of radiation is incident on matter. The energy absorbed would then be given by the equation E is equal to h nu. E is equal to h nu is the fundamental equation of spectroscopy. What is E here? It is the energy of photons absorbed in ergs or joules. Okay, it is the energy of photons absorbed. What is small h? This is small h. What is small h? It is Planck's constant. And what is nu? It is the frequency of radiation. Nu is the frequency of radiation in hertz. Now E equals h nu, but we also know that from the velocity equation, we know that velocity in vacuum C equals lambda nu. Hence, nu could be written as C by lambda. So if we substitute this value of nu in equation 1, then we get E is equal to hc by lambda. And what is 1 by lambda? It is wave number. So E can also be written as being equal to hc into wave number. So from these two equations and also this first equation, what we realize is energy increases with increase in frequency and wave number, because wave number is directly proportional to energy. Frequency is also directly proportional to energy. When frequency increases, energy increases. When wave number increases, energy increases. But energy increases with decrease in wavelength, because you come to this equation, you see E equals hc by lambda. That means when wavelength increases, the denominator is increasing, then the ratio, that is E, will decrease. That is why when there is a decrease in wavelength, the energy will increase. This is an inverse relationship. So always remember, energy has an inverse relation with wavelength, but a direct proportionality with frequency and wave number. So our next topic is electromagnetic spectrum. So the spectrum is the written records of electromagnetic radiation. Electromagnetic spectrum is divided into different regions based on the type of atomic or molecular transition that gives rise to the absorption or emission of photons. I hope you understood this. The whole region of electromagnetic spectrum is divided into different regions, which are based on the type of atomic or molecular transition that gives rise to absorption or emission of photons. Transitions usually refer to changes in energy levels. The boundaries describing the electromagnetic spectrum are not rigid, and an overlap between spectral regions is possible, because you will now be seeing that one region extends from so many nanometers to so many nanometers. Doesn't mean it's a strict boundary. The boundaries are always overlapping. So this is a pictorial representation of electromagnetic spectrum. So you have all these regions in your electromagnetic spectrum. You have radio waves, microwaves, infrared, and this, of course, is the visible radiation, ultraviolet radiation, X-rays, and gamma rays. It's a good representation which indicates a number of things. You see, here are the wavelengths given. This is the range of wavelengths, okay, approximate range of wavelengths. For example, like visible radiation or UV radiation extends from around 10 nanometers to around 400 nanometers, and visible radiation from 400 to 800. This is approximately 1000. This is the infrared radiation. You can also see from here in this picture, you see the wave here. Notice the wave, and it becomes very close. So what does it indicate about wavelength? The wavelength is the linear distance from one point of a wave to the corresponding point on the adjacent wave. From one point of this wave to the corresponding point on the adjacent wave. So you can easily make out that the wavelength on the right hand side for, say, for the gamma rays is very small. It goes on increasing as you proceed to the left, and it is maximum for the radio waves. The top side is something what it is used for. The radio waves are used for radio purposes, FM, AM, TV, radar, etc. And in between you have the microwave, you have the microwave ovens. Then you have the infrared, where you have your TV remote has always an infrared lamp. Then you have the light bulb for the visible region, ultraviolet, sun has emits ultraviolet radiation, X-rays, you all know about X-ray machines, X-ray films, so X-ray scans that many have to undergo for detecting certain diseases. And you also have gamma rays. These are the radioactive elements which emit gamma rays. Now what you see at the bottom here is just descriptive about the wavelength. If gamma rays have a wavelength which, say, corresponds to an atom size, then radio waves have a wavelength corresponding to the size of a building. Huge difference between the wavelengths of gamma rays on one end to radio waves on the other. I hope this makes it very clear to you about the various regions as well as the wavelengths. What about the energies? When you are telling this is the wavelength, which has more energy? Of course, the gamma rays, because I just told you energy is inversely proportional to wavelength. Wavelength is shortest for gamma rays, and therefore its energy will be the highest. Whereas radio waves have got the longest wavelength, so its energy will be the least. So this is another explanation. Another representation you can see here, you have gamma rays, X-rays, UV, this part is visible, IR, microwave, radio wave. Here also you have the wavelength regions, this is in meters and this is the frequency values. These are all approximate values. So roughly around this values. The more important in this particular picture is visible radiation is divided now into a number of colors, as you see, and each of these colors correspond to a particular wavelength. This is measured in nanometers. Now, another thing is the type of transition involved. If you are dealing with gamma rays, then it will be nuclear transitions. If you are studying using X-rays, then core level electrons or the inertial electrons are the ones which will result in transitions. And if it is UV or visible, it's the valence electrons. If it is IR, it's the molecular vibrations. And if it's microwave, it's the molecular rotations or the electron spin. And if it is radio waves, then it is nuclear spin. Because lesser energy can bring about only so much, whereas gamma rays, nucleus itself undergoes energy transitions. Here it is the spin which will get affected. Another way of representing, here you have the frequency range also in hertz. It's not necessary for you to remember this. Maybe you can approximately try to remember the wavelength range, but you should remember the type of radiations and the type of transitions. So you start with gamma rays, the most energetic type of transition, nuclear. X-rays, inner electrons. Ultraviolet, outer electrons or valence electrons. Visible, outer or valence electrons. Near infrared, because you will see in infrared spectroscopy, it is two different types, near infrared spectroscopy and infrared spectroscopy. You also have far infrared too. But near infrared, it's the outer electron molecular vibrations, and infrared, it's only molecular vibrations. Far infrared actually goes for molecular rotations. Then you have microwaves which deal with molecular rotations and electron spin flips. Radio waves deals with nuclear spin flips. You will be studying each of these in the different spectroscopy that you have in your syllabus. This is the visible region, again highlighted as number of colors. These are again the same thing in indicating the wavelengths, frequency, energy. So we are more concentrating in this chapter on UV visible. So you can see the energy also, it is highest for 10 raised to 13 for the gamma rays and lowest for the radio waves, 10 raised to minus 11 in kilocalories. So considering the UV visible region, the UV region can be divided again into two parts, that is vacuum UV and UV. Vacuum UV extends from 5 to 200 nanometer, whereas UV extends from 200 to 380 nanometers. This is the part which will be used extensively in absorption spectroscopy. And why this difference is done is because below 200, air starts absorbing UV radiation. So if you want to measure absorptions of radiations having wavelength less than 200 nanometer, then the measurement has to be done in an area where vacuum is created or which is devoid of air. That's why the region below 200 is called the vacuum UV region. So since it is not as convenient as the UV measurements, the UV measurements are more popular compared to vacuum UV region. The visible spectrum, on the other hand, is sandwiched between the infrared region and the ultraviolet region. Ultraviolet region is the more energetic region and infrared the less energetic region. So above 780 nanometer, basically visible spectrum extends from 380 to 780 nanometers. So after UV, you have 380 to 780, and infrared starts from 780 nanometers onwards. So you will be seeing something like 0.78 microns will be the starting wavelength. Now, when we are talking about visible lights, there are a number of colors in visible light. You all know white light is made up of a number of colors. So the wavelength of maximum absorption. Now, there are two types of colors. When you are talking about absorption, what color you see? Say you have a yellow colored solution, then it means that the color that is transmitted is the color that you observe. Okay, so if you're seeing a yellow, or we'll take the purple solution, you all know potassium permanganate. Potassium permanganate is purple in color. Okay, now if you want to do a absorption spectroscopic study of potassium permanganate and you want to determine its concentration, what is the wavelength of radiation you will make incident on a purple solution of potassium permanganate? You will make 500 to 520. This region actually corresponds to green color, because purple solution will absorb its complementary color green. It will not absorb purple. So if your solution is looking purple, you have to use the wavelength corresponding to the complementary color. Complementary color for purple is green, and hence you will use a wavelength of 500 to 520. On the other hand, if you have a green solution, you will use the wavelength corresponding to purple color, because that's the complementary. I hope it's understood. So these are the various ranges. If the absorbed color, what is the absorbed color? You use a corresponding wavelength for studying a green, yellow, or the transmitted color. These two colors, absorbed and transmitted, are complementary colors. Interaction of electromagnetic radiation with matter. This is our next topic. So, because we started off with spectroscopy and we said that it is a branch of science that deals with study of interaction of electromagnetic radiation with matter. So, when electromagnetic radiation falls on matter, what type of interactions take place? First possible phenomenon is the electromagnetic radiation may be absorbed by matter. So it results in absorption of electromagnetic radiation. If this happens, then within a short time, the absorbed energy will be released by matter, because it cannot store that excess energy. So it releases and you get an absorption spectrum. We will be going into this in detail because this is what relates to our chapter. Second possibility is, suppose absorption is not occurring. The radiation may be scattered or reflected. This happens, and the study of this scattered radiation constitutes nephoturbidimetric method of analysis. It's also a spectroscopic technique that is used to study heterogeneous mixtures, or you can say biphasic or triphasic systems. You can use it to study suspensions, emulsions, colloids, etc. So here what happens is, since particles will be suspended in a medium, when radiation falls on the particle, it gets scattered or reflected. The scattering or reflection depends upon the wavelength of radiation and the particle size of the suspended medium. If neither absorption nor scattering is taking place, one more possibility is the electromagnetic radiation may undergo a change in orientation or polarization. This you'll be studying under the chapter polarimetry, and this is seen in case of optically active molecules. And the last phenomenon which can take place is sometimes after absorption of radiation, there is immediate release of the excess energy doesn't take place. There is a time delay, and after that, electromagnetic radiation may be emitted, thereby releasing the excess energy. So the excess energy may be released by emitting secondary electromagnetic radiation. This comprises fluorescence or phosphorescence, and this again you will be studying in detail in fluorimetry. What is the difference between the two, etc. So this is emission phenomena. So these are the four possibilities that can take place when electromagnetic radiation interacts with matter. Each of these you will be studying more in detail in the concerned chapters.